One by one, you collect pairs of numbers. These are the data you will be analyzing as a data analyst. Maybe it's the energy consumption of a robotaxi versus its speed. As the numbers pile up, you notice a pattern emerging. The data appears to follow a line, but it's not perfect. There's quite a bit of noise. What do you do when the data wants to form a line, but doesn't quite get there? That's where linear regression comes in. By the end of this lesson, you'll know how to take a messy cloud of data and find the line that fits it best. A best fit line, if you will. We'll show you how to measure the quality of the fit, minimize the errors, and calculate the equation of that line. Suppose you've collected only 2 data points. You can always draw a line that passes perfectly through both of them with very little difficulty. But what if you have more than 2 points? Say, 3 points that don't line up perfectly? Now you've got a problem. If you pick any 2 points and draw a line through them, you get a perfect fit for those 2. But you completely miss the third. So what do? We need a line that doesn't pick favorites. It should pass as close as possible to all of the points, even if it doesn't go through any of them. The solution? Linear regression. This method finds the equation of the line that is the best compromise. To find the best line, we first need to decide what best means. In other words, we need a way to measure how much the line misses each point. There are a few ways to do this. We could measure the vertical difference, the horizontal difference, or maybe the shortest distance from each point to the line. But since we treat the x values as inputs and the y values as outputs, we'll focus on the vertical difference, how far off the predicted value is from the real value. Now, here's the twist. We don't just add up those vertical misses. We square them first. Why? Well, squaring makes all the errors positive and gives more weight to bigger mistakes. But more importantly, if the errors follow a normal distribution, minimizing these squared errors gives us the line statistically most likely to represent the data. This is why the standard approach is called the method of least squares. If this lesson on regression sparks a session of reflection or leaves an impression worthy of confession, consider a profession of support at Patreon. The equation of the best fit line takes the form y equals m times x plus b, where m is the slope and b is the y-intercept. Once we have the values of m and b, then we'll have our working equation for the best fit line. Let's first calculate the squared errors for our 3 data points. We'll start with the point -1, 4. To get the predicted value of y, we plug -1 into our equation. We don't know m or b yet, so we leave it as an expression. Now compare this to the actual value of y, which is 4. Take the difference to find the error, and then square it to get the squared error. That completes the first row of our table. We'll do the same for the next 2 points. Finally, add all 3 squared errors together. If we expand and simplify, we get the following expression for the overall sum of squared errors. That's our score for how badly the line fits. Lower is better. You can think of this error expression as a function of 2 variables, m and b. Since there are 2 inputs and 1 output, we can graph this function in 3D space. This gives us a smooth, curved surface. Remember, our ultimate goal is to find the best fit line for our data points, the line with the smallest error. And the smallest error occurs at the lowest point on this surface. This calls for a little calculus. At the lowest point on a surface, the tangent plane is level. This happens when the partial derivative with respect to m is 0, and the partial derivative with respect to b is 0. We now have a system of 2 linear equations with 2 unknowns. You could solve it by hand with substitution or matrices, or you could let software do the heavy lifting. Either way, you'll find the slope is 1/3 and the y-intercept is 11/3. This gives us the equation of the best fit line. And for the pièce de résistance, we plot it. This best fit line doesn't go through any of the data points, but it stays close to all of them. It's not perfect, it's just the best you can do. And that's exactly the point. It took a lot of steps to find the slope and y-intercept of the best fit line, but broadly speaking, there were 2 big ideas at work here. 1, measure the error between our line and the data, and 2, minimize the error. It turns out that if you repeat this multi-step process in a more general way, you can come up with general formulas that will provide the essential ingredients of the best fit line, the slope and y-intercept. The slope is the covariance of x and y divided by the variance of x, and the y-intercept is the average of the y values minus the slope times the mean of x. Why didn't we just hand you these formulas from the start? because the real value here isn't just in knowing the answer. It's in understanding how we break down a problem, measure the error, then minimize it. That's a problem-solving approach you can use over and over again, whether you're doing more complex regressions in math, science, or even AI. Let's demonstrate these newly revealed formulas with our 3-point example. First, we find the average of the x values and the average of the y values. Then we calculate how much x and y vary together. That's the covariance. How much x varies on its own. That's the variance. Once we have these pieces, we just plug them into the formulas. We get the same line we found before. Let's look at a more realistic example from the world of AI. Large language models respond to prompts. You can measure the length of these prompts in tokens. Tokens aren't quite words. They're chunks of text, a word or part of a word. The more tokens you send, the longer the model takes to respond. It's not perfectly predictable, but there's a clear trend, which makes this a great use case for linear regression. We collect data. On the left, we list 20 prompts with their lengths in tokens and response times in milliseconds. On the right, we plot those points. It's not a perfect line, but there is a pattern that does look linear. Let's find the best fit line. First, we calculate the mean of the inputs and outputs, the average number of tokens, and the average response time. Then we compute the covariance, how the two move together, and the variance of the input. Now we apply the formulas. Plugging in the numbers gives us the slope m and intercept b. These allow us to write the equation of the best fit line using the method of least squares. Now we plot it. Finally, let's put our newly found line to work. One of the benefits that comes from having a best fit line is the ability to make predictions. Suppose a prompt has 1,000 tokens. How long will the model take? If you plug in 1,000 and evaluate, we get our estimate. You can imagine reasons why it's good to know how long something will take in terms of planning, energy needs, and so on. Linear regression worked a treat for our LLM problem. But will it work for any dataset? Let's investigate. On the left, a dataset with 20 points. On the right, a scatter plot of those points. You might notice right away, this doesn't look like a line. It curves upward, then downward, a classic U shape. This is an important step in data analysis. Inspection. Is the trend linear? No. So linear regression is probably not the right tool here, but let's try it anyway. We run the same formulas as before, and plot the line. It's not great. The line cuts through the middle, but completely misses the shape of the data. The fit is weak, and the error is large. Can you see why it's essential to look at your data before applying a model? There's nothing wrong with the linear regression formulas. They simply are not appropriate for this situation. Even a correct calculation can give a wrong answer if the model doesn't match the shape of your data. But don't worry, there are other kinds of regression for curved data. One such method is polynomial regression, fitting a curve instead of a line. This data came from a noisy parabola, and the best fit parabola captures the trend remarkably well. The key is knowing that regression isn't one size fits all. Linear regression works beautifully when the trend is straight, but when it's not, be ready to try something else. If you'd like updates when we launch a course or start a new series, sign up for our mailing list. Our emails are tastefully infrequent. There's a link in the description. There's also a description in the description.